Okay, hello everybody. My name is Dmitry. I'm the moderator for today's talk. And today, Michael Wormit will be giving a second part of a seminar on the symmetries, which is called Symmetries in Quantum Chemistry. So more general symmetries, more theoretical talk. So Michael, please go ahead and tell us about symmetries in quantum chemistry.
All right. Yeah. Thank you, Dima, for this nice introduction. Yeah. So I'm going to talk about symmetries in quantum chemistry, and if there are questions, please feel free to ask even during the talk, so I can answer them, and there everything is clear. I hope I can give you an overview of what symmetries in quantum chemistry are, what the important pieces are. And I'm leaving out any connection to libtensor because I figured it's going to be far too much for just one talk to cover all of the symmetry here. All right, so a very brief introduction. Well, symmetry is central to all of physics, and probably the most important theorem about symmetry in physics is the Newton's theorem in classical mechanics, where they say that every continuous symmetry property of a system is associated with a conservation law. So that's like translation invariance and conservation of momentum, rotational invariance, conservation of angular momentum, and some other symmetries. For quantum field theory, there's an equivalent for that, which is called Ward-Takahashi identities, which I've never heard of before I prepared this talk, but I thought it would be an interesting information for that. These same things which exist in Newton's theorem kind of transfer to quantum mechanics, where we represent symmetry in terms of operators. So, for example, for the hydrogen atom, you have also this rotational invariance, which is related to the conservation of angular momentum, and more specifically in quantum mechanics, you have this the eigenfunctions of the hydrogen atom. The electronic eigenfunctions are also eigenfunctions of the angular momentum operators. And this is what this whole talk is going to be about, the operators and how what we can learn, or how we can use the symmetry in quantum chemistry. So therefore, we start off. I start off with explaining a central theorem in quantum mechanics or quantum chemistry, which is about two commuting operators. So two operators which commute possess the same set of eigenstates. And to rationalize this, we assume like we have two operators, A and B, which commute. So the commutator is 0. And we have a set of eigenstates for one of the operators, A, which is like the right equation. And then we just apply, reformulate. So we apply both A and B to psi I, the eigenstate of A. And then we use the commutation relation to swap these two around. That's the first identity. And then we directly see, all right, that's applying A onto psi I, we get the eigenvalue and the eigenvector. And then just putting a few brackets on the left and the right part, the left-hand side and the right-hand side of the equation, we see that now B psi I is also an eigenstate of A. So this psi I tilde, which I call it here, is an eigenstate of A as well. And then, like if AI is non-degenerate, so there's only one eigenfunction which relates to AI, then this psi I tilde must be proportional to psi I, from which follows that B psi I, so psi I tilde is a multiple of psi I, which is again where you see that's again the eigenvalue equation. So psi I is also eigen vector of B, same as of A, but with different eigenvalues. All right, second case would be AI is degenerate, and then one can show in a few steps that you can linearly combine the degenerate eigenfunctions or eigenstates of A into a state chi, which is then in turn an eigenstate of B. That's a bit messy to show this, but it's not a problem. Essentially, what you do is you build up your matrix Cik, and then you get a system of linear equations for this matrix. And there's one condition for these matrix elements, which are that this matrix Cik is unitary, and you can directly show that this is the case, and this is more or less a sketch of the proof for this theorem. Anyways, I mean, this has, like, at the moment, this has nothing to do yet with symmetry, but now let's consider what are the consequences for of this theorem for the Hamiltonian, assuming that we have a set of operators AI, which we assume being symmetry operators. So, for example, could be the S squared, so the spin operator, and the SZ operator, or permutation operators. So assuming they commute with each other, so for example, S squared and SZ would commute with each other, and they also commute with a Hamiltonian. And then if they commute with each other, then we can build up a set of eigenstates for the AIs, which I call psi k alpha, where alpha indicates the degeneracy of the eigenstates. Down here is also the eigenvalue equation. So, and then what we can do with these states, I mean, they form, assuming they form a complete basis, then we can form eigenstates of H from these psi k alpha by doing a linear combination. That's what was the previous theorem just about. And these are now eigenstates where the index of the eigenstate, so k, refers to a specific eigenvalue of the previous operator, and R is just the linear combination of well, there are various linear combinations if degeneracy. So this is the two indices of this for the eigenstate of the Hamiltonian. Yeah, so that's how we construct an eigenstate. And now, if we take this this eigenvalue equation for the Hamiltonian and project onto the eigenstate functions from the symmetry operators, we see that in the result we get, after like 2 steps, we get a delta k prime, which means that for an eigenstate of the Hamiltonian, there are only components in there which belong to one degenerate set of eigenstates of the symmetry operators, which results in such a block structure I've printed here for the Hamiltonian. So I've like to explain this picture. You have on the axis the eigenstates of the symmetry operators, which are indicated by k and alpha, k prime alpha, and k double prime alpha. So k are like the alpha indicates the degeneracy again, and k prime, k double prime refer to different eigenstates, to different eigenvalues of the or to eigenstates belonging to different eigenvalues of the symmetry operators. And with respect to this basis, the Hamiltonian is block diagonal in so there's only non-zero elements within the same K. And this is one of the main ways to look at symmetry. It's like in this way, if you have operators which commute with each other, the Hamiltonian, expressing the Hamiltonian in the basis, in an eigenbasis of the symmetry operators, you get automatically a block diagonal structure out of this for the Hamiltonian. And then you can just, if you want to solve now for the eigenvalues, you can just concentrate on one of these diagonal blocks and solve them independently of each other. And this is what you always do in any quantum chemistry program. If you have spin symmetry, point group symmetry, you calculate the singlet state with, if you have, for example, C2V point group symmetry, irreducible representation A2 or so, and then with B1, and maybe you do the triplet state and so on. So this is where this block structure comes from. There's, however, a different view, especially which is particularly important for point group symmetry, different view on the problem, and therefore we consider now, assuming we have a group of transformations G with elements which refer to, for example, like for point group symmetry, would be rotation by 180 degrees, or an inversion with respect to the origin, or a mirror plane, or something like this. So G would be an operator which translates a function accordingly, like it mirrors it along the xy plane or something like this. And these elements do not necessarily commute with each other. That's, they commute if you have an abelian point group, so C2V would be an example where they commute. But for example, if you have C3 symmetry, like boron 3 molecule which has C3 symmetry, there they wouldn't commute, because if you have a rotation by 60 degree, this is the one symmetry element, this doesn't commute with the rotation, with the rotation by, now I'm lost. I think it's 100 degree. Oh yeah, with the mirror plane, which you also have in the boron atom, boron molecule, boron 3 molecule. So that would be an example where where elements don't commute. But each of these elements commutes with the Hamiltonian. And what you can do now is you can use this commutation relation and just reshape it into by adding h times g and getting it onto the other side, and then multiplying by the inverse of this transformation. And then what you see is that the inverse of the commutator relation now looks like a transformation of the Hamiltonian, and this last equation essentially says that the Hamiltonian is invariant under transformation of these group elements, or it is totally symmetric with respect to the elements, or another way of saying it would be it belongs to the totally symmetric irreducible representation, or it transforms like the totally symmetric irreducible representation. All right, and the consequence of this is that for any eigenstate psi k of H with eigenvalue ek, where the Q as also again indicates degeneracy if it's present, you can look at the state, the transform state. The state transforms with respect to G, and this is also an eigenstate with the same eigenvalue ek of H. You can show this by just similar to before, by just applying the Hamiltonian and using the commutation relations. And now what you can do is you can write down G as a linear G applied to psi k as a linear combination of other case with the same psi case with the same eigenvalue. And here, these factors are usually called it's a representation of G. And in particular, this G is an irreducible representation apart from if there are accidental degeneracies in the Hamiltonian, where you have identical eigenvalues, although they there is no symmetry reason for them, which might happen eventually. Oops, sorry. Yeah. So, and since this is an irreducible representation, what you see is that the eigenstates of H transform like the basis function of the irreducible representations. This is this formula up there with the G psi equals the sum. This is just completely identical to the transformation rules for the basis function of the irreducible representation. That's yeah, that's more or less the definition. Yeah. So, and these are the two viewpoints. Sorry, for symmetries, and now I come to the to some more concrete examples for symmetries. And what are those? Well, one of the main symmetries we kind of like always have included, and we only care we care about it in the derivation of all of our equations, but later on we don't bother with them anymore, is particle permutation symmetry. Well, particle permutation is concerned with a permutation operator, Pij, which permutes two particles with index I and j. And well, if you do this twice, then you should get the original, if you apply this operator twice to a wave function with many particles, you should get the same wave function out. So permuting I and j and doing the same thing, you get a more or less the identity operator out. And from this, we can directly deduce that the eigenvalues of this permutation operator are just can only be plus or minus 1. Since if I apply Pij squared to psi k, well, that would be for if psi k is an eigenfunction or an eigenstate of Pij, then you would get a pk square out of this, and this has to be 1. So pk squared is 1, and then the only two solutions of this equation can be plus or minus 1. And the eigenstates are then the bosonic solution or the bosonic state or the fermionic state. So if pk is, so if the eigenvalue of Pij is 1, then you have bosons, like a many particle function of bosons. Or if it's the minus 1, then the eigenstate is antisymmetric with respect to particle exchange, and then it's fermions. And the Hamiltonian commutes with the Pij, and if the particles are indistinguishable, which they always are in our case. So you get two sets of solution for the Hamiltonian. That's this block structure again. One is the bosonic and one is the fermionic, and we always only are concerned with the fermionic ones. So this is more or less intrinsic in all our approaches. So the state determinant is the fermionic one. That's we more or less put this directly in. Another important symmetry is spin symmetry. There we are concerned with the operators, the spin operators, which is s squared and sz in this case, and they both commute with each other. So we can use this theorem, which I presented in the beginning of these two operators, like if the operators commute with each other and with a Hamiltonian. And well, we can now construct for these two operators eigenstates and eigenvalues. And there's a standard way of doing this, and you have then usually the S eigenvalue and the MS eigenvalue, where S is the eigenvalue for the S square operator, or almost, and MS is the eigenvalue of the SZ operator. Here I print the eigenvalue equation as well. And and for spin-independent Hamiltonians, you have also the commutation relation, so they commute with the Hamiltonian, and thus you can solve the Hamiltonian for each S and MS system separately. So you can solve for singlet, for triplet, and for example also for high spin triplet, or whatever you fancy, and depending also on your system. I mean, if you have 2 electrons, you can only go up to triplets at maximum. But if you have more, then you can have also like quintets, heptaplets. I have problems at some point getting the names right. So this is more or less what there is for spin. I can say something later on how you construct these eigenstates and eigenfunctions for the spin operator. But now let's go for the third, probably the most important and also like the most difficult part of or symmetry type, which is point group symmetry. There, the operators are the group operations like rotation, mirror, inversion. That's most of them. There's some very, very rare symmetry element as well, which is like a helical rotation, like rotation and translation sometimes. But that's more in crystals, I think. I've put here an example for a molecule which is like a water molecule, which is C2V symmetry. So this has a rotational axis which is in the plane, in the plane of the screen, going through the oxygen atom, and has 2 additional mirror planes. One is the screen plane, and the other one is perpendicular to the screen plane through the oxygen again. And this is an abelian point group. So for these 3 operations, so the rotation around the z-axis through the oxygen atom by 180 degrees, the mirror plane and the 2 mirror planes are all operators which commute with each other. So there's a common set of eigenstates, and we could go forward as we did with the spin. So construct these eigenstates and have the block structure right away out of the algebra, operator algebra. If you don't have point groups, abelian point groups. Sorry. Then you would have to form states or basis functions which transform like the basis function of the irreducible representations of the group. In the case of the abelian point groups, these are just the eigenstates, but like for non-abelian ones, you would have to construct these states which you which transform accordingly. So that would be what would these states be? For example, in case of the water molecule, like you have for C2V, you have the totally symmetric irreducible representation. So that would be the application of every operation on a basis function which belongs or is associated to this totally symmetric irreducible representation would map the irreducible representation onto itself. So that would be, for example, a spherical function on the oxygen atom would be of the totally symmetric irreducible representation. Other irreducible representations, I would have to think about how they would look like. So probably you could also construct something like a two spherical functions on the hydrogen atoms that these would still be totally symmetric with respect to all three operations. If you add a phase factor to this, then you have some antisymmetry with respect to the rotation. So if you have if you would have a function which is positive on one hydrogen atom and negative on the other one, you could you have a sign change when you do the rotation and the mirror perpendicular to the screen plane. Yeah. So, and these functions you have to construct from your basis sets in our case, and then you can group these functions according to the irreducible representation they belong to, and then it's sufficient to solve to diagonalize the Hamiltonian in the set of these functions, because only functions belonging to certain irreducible representation. So only functions belonging to one irreducible representation contribute to a certain eigenstate of the Hamiltonian, which also then belongs to this irreducible representation. Which means that again, the Hamiltonian is block diagonal in this state basis, and we can solve one after the other. But so this so far for the Hamiltonian. But what about other operators? Here, let's consider a really simple example, because I really have problems in drawing like 3D pictures for this in this case. So consider we have a system which has a mirror plane along the y-axis, just a one-dimensional system, and then you can have two functions, the gerade function and the ungerade function, or even an odd function. I've plotted one on the right and one on the left. So these are just two possible functions. There are many others. And now what happens to a matrix element of an operator? And as an example, I have used the X operator, which is the typical operator for dipole transitions. So this would be a matrix element if you wanted to calculate the dipole, the probability of a dipole transition from one state to another. And well, here you see the integral, how it looks like, and now what the integral kernel is like the product of the gerade function, the ungerade function, and the x function, which is also an odd function with respect to the mirror plane. And I've plotted this the product function in the middle below, and you see, so the integral, if you do the integral over both, that's non-zero. But for example, if you would have like two gerade functions and the x, then this mirror function would look like just one side of these peaks would point down, and then the integral on the negative x-axis and on the positive axis would be opposite signs, so the sum of the two would be just 0, and you would get a 0 element matrix element out of this. So from this you can see, all right, this matrix element is non-zero only if the integral kernel you are integrating over is gerade or totally symmetric in this case. And this is the general rule as well for non-zero matrix elements, and how you make use of symmetry, of point group symmetry for other operators beside the Hamiltonian. It's just you look at the integral, you have to evaluate and see what is the direct product of the irreducible representations of the objects you are which are contributing to this integral or to this matrix element. And if these three, in this case for this for one particular operator, if the direct product of the three irreducible representations associated to the objects, so in this I've denoted the irreducible representations below here as gamma. So if gamma alpha, so that's the irreducible representation related to psi alpha, the gamma O is related to the operator, and gamma B is related to psi beta. If this contains the totally symmetric irreducible representation, then a matrix element is non-zero. And this to get this direct product, or to evaluate this, you can look up at the product tables for any point group. They are available on the internet, and there's also a way how to calculate this, but this is going much deeper into point group symmetry than I wanted to go today. So if this is the case, then you can neglect these matrix elements. And this way, again, these operators become a block structure for which is not necessarily block diagonal anymore, but there are a lot of non-zero, a lot of zero blocks if these products of three elements, three irreducible representations are don't contain the totally symmetric irreducible representation. And with this also the you get the similar selection rules. So you have for electronic transition, for example, you have you have usually dipole transitions using the dipole operator, which is just the X operator with some prefactors, and then well, X operator doesn't contain spins, so you don't have spins change. And then you usually refer to Fermi's golden rule, which says that the transition probability between two elements, between two states, is just proportional to this matrix element, which I've drawn here, where psi 0 is the initial or the ground state, and psi f is the final state in which you're going to. and the matrix element has to be non-zero for the transition to be allowed. And yeah, and there's this again, you use the irreducible representations of the two of these two states and of the operator, and can already see from the product table of the point group symmetry, for example, if the this matrix element is allowed or not. And this is, I think, more or less all I wanted to say.